Hi guys, myself Pranav is here to deliver today's presentation, Power Transformer Part 58. As the subject is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with classification of transformer insulation system. Transformer insulation design and insulating material selection both would have been the most crucial analytical process to derive with numerical classifications based on the successive pattern of temperature rise in respect of actual position and placement of the components. Key components are to be sorted out by means of energy as dissipated in the active parts of the transformer such as windings, core and surrounding structures. Total energy loss in transformer active part would be a combination of 4 types of losses, and altogether that leads to an undesirable heat loss. Types are as follows: 1. Copper loss, number 2. Eddy current loss, hysteresis loss, flux loss. Energy losses due to the DC resistance in the primary and secondary windings are to be termed as copper loss or I square R loss. Eddy current loss and hysteresis loss in combination would be termed as core loss, and that has to occur in the ferromagnetic core circuit due to have the process of alternating magnetization, and that leads to generation of heat within the core. Coal loss or iron loss in a transformer is rather a no load loss, that is regardless with variation of load, and is referred as constant loss. Again I repeat, coal loss or iron loss is in a transformer is rather a no load loss, that is regardless with variation of load, and is referred to as constant losses. Whereas copper losses, as would have to vary with the square of the load currents, so it is referred as variable loss. Therefore, coal loss or iron loss is a constant loss, and copper loss is a variable loss. It is important to note that about 90% of the total transformer losses would be rather contributed through the copper losses or load losses. That is, variable loss is about 90% of the total transformer losses. Flux loss is an important parameter for energy loss in a transformer, which would have to occur due to leakage flux, as when some of the flux lines from the primary do not pass through the core to the secondary, resulting in a power loss. Leakage flux is therefore be a fraction of the total flux, which may have to follow a path through air, and that would thus to produce eddy currents in the conducting or metallic parts like tank of the transformer. On other way, occurrence of leakage flux might have been caused due to the imperfect coupling between the primary and secondary windings. The power loss as caused by the eddy currents flowing through the conducting components other than windings of the transformer is termed as stray loss. Major flaw in physical designing of the transformer would have been the main contributor for producing these leakage fluxes, which includes a the incorrect distance between the windings, the improper material properties of the core and windings, improper frequency and magnitude of the current passing through the windings. These three are the major flaw during physical designing of the transformer. Stray losses can be countered by providing electromagnetic shielding in the transformer tank. However, elaborate discussion has already been made regarding the various provision and application of electromagnetic shielding in the previous slides. Stray losses, as it is comparatively much less than that of due to iron loss and copper loss. So, it will not affect the overall transformer efficiency. Dielectric loss. It has already been understood that operating temperature is one of the most important elements to determine the operational reliability of a power transformer. Low operating temperature is actually be much more prudent on maintaining various dielectric properties of the insulations as contained within the solid and liquid insulating materials. Under low operating temperature, life of the transformer that would also to be further extended with having an enhanced efficiency throughout its operating span. Significantly, high operating temperature can obviously lead to higher dielectric losses. Dielectric material is to be referred as an insulating material which has to contribute poor electrical conductivity, and that basically contains no free electrons. That is within the basic structure. Dielectric materials, though, have to transmit an electric field but do not conduct electricity. Dielectric materials, though have to transmit an electric field but do not conduct electricity. It means that the dielectric materials would have the characteristics of transmitting electric effects without conducting. Dielectric materials can have the excellent ability to support the electrostatic fields and to store electrical charge as due to the phenomenon of dielectric polarization. Dielectric materials may possess high specific resistance and have negative temperature coefficient of resistance. Temperature coefficient of resistance for a material can be justified by its resistance change factor per degree Celsius of temperature change. A negative temperature coefficient of resistance for a material that has to specify with the decrease of its resistance with an increase in temperature. That is the reason negative temperature coefficient of resistance. Dielectric strength of a material would be determined by its dielectric constant. Dielectric constant of a material is thus to be referred as the measurement of its ability to store electrical energy. A material with high dielectric constant can have to indicate that it has to store more electrical energy than that of a material with low dielectric constant. Dielectric constant of a material can be expressed by the ratio of a permittivity of the material to the permittivity of free space. In case of alternating current equipment is concerned, the dielectric constant of material as used for would be selected with a number that relates to the ability of the material to carry alternating current to the ability of vacuum to carry alternating current. Again, I repeat, in case of alternating current equipment is concerned, the dielectric constant of material as used for would be selected with a number that relates to the ability of the material to carry alternating current to the ability of vacuum to carry alternating current. The effect of temperature on dielectric constant is an important issue for selection of the dielectric material, as because the dielectric constant is inversely proportional to the temperature. The dielectric loss would therefore be increased with the increase in temperature. As the mobility of charge carriers within the structure of the material increases with temperature, so the incidence of dielectric polarization can have to be instigated, and that leads to high dielectric loss. The dielectric strength of an insulating material that refers to an ability of withstanding the maximum electric field under ideal conditions without undergoing dielectric breaking down or becoming electrically conductive. Again, I repeat, the dielectric strength of an insulating material that refers to an ability of withstanding the maximum electric field under ideal conditions without undergoing dielectric breakdown or becoming electrically conductive. Under the impulsive action of an electric field and subject to the hysteresis effect of dielectric conductance and dielectric polarization, there would have been an energy loss inside the insulating material. Complexity in power transformer insulation system. Insulation system to power transformer is one of the most prime component for determining the long-time reliability and highly efficient operating characteristics. The two-phase insulation system, that is oil and cellulose, has the usual composition of designing transformer with the higher capacity and voltage level. So for the high availability of cellulosic paper and mineral oil in combination is not only cost effective, but would have to form an excellent insulation performance. Cellulosic paper and mineral oil. The internal configuration of power transformer as being comprised of different types of materials. So, at the operating environment, these materials would have to suffer a constant phase of unusual constraints like the chemical, mechanical, electrical, magnetic, and thermal stress. Under the influence of such stresses and due to presence of oxygen, moisture and contaminants, the insulation would have to deteriorate, though slowly but continuously over a period of time, eventually leading to catastrophic failure. Technically, this has already been established that life of the paper insulation is typically the life of the transformer. Most important. Most important to note, life of the paper insulation is typically the life of the transformer. Adequate insulation is not only an obligatory or mandatory requirement to isolate the primary and secondary coils from one another or from the core and tank, but also inevitable to ensure the safety of the transformer against all sorts of voltage surges. At the present context, requisite insulation system as designed must have to satisfy both electrical and mechanical properties at elevated temperatures. So, high thermal stability would have become the prime necessity for better longevity and predictable lifespan of the insulating system. Thereby, special emphasis is put on the strategies to upgrade the material composition of the insulation system. Insulating material are essentially of non-metallic, organic, or inorganic type, uniform or heterogeneous in composition, natural or synthetic. An ideal insulating material should have high dielectric strength, high resistivity, good thermal conductivity, high tensile and shear strength, high degree of thermal stability. For oil field transformers, material must be of oil resilient type. That is, solid insulation material must be of oil resilient type. The insulation design of power transformer that corresponds to the basic criteria of considering the maximum values of voltage or current to which the device will be exposed during operation. There would have been daunting task to characterize a sudden change in a system condition due to lightning or switching surges or occurrence of line faults, which corresponds to electromagnetic transient phenomena. Electromagnetic transient, though its time period is comparatively very short, but during this period, the system components are exposed to severe stresses from excessive voltages or currents. Matters are also to be noted that a power transformer may have to undergo continuous exposure to voltage pulses and for which can result in partial discharges, high electrical stresses, abnormal heating, etc. All these happenings are quite related to premature aging of the transformer insulation system and that must be seriously dealt with during selection of insulation materials as well as their class of insulation. The relative permittivity of the insulation materials are of great importance for the adequate performance to counter the subsequent effect of maximum electric stress as developed in the internal part of the transformer components. It is also to be considered that the components would always be exposed with variable electric potential. Dielectric strength of the insulating material that would have to influence the direct effect on the size of the transformer winding. Main perspective of insulation design is thus to be framed in such a way that the transformer must have to be operationally safe and reliable even at high operating temperatures and high electrical stress. Transformer insulation structure that would have to differentiate in two parts. One is the major insulation structure and number two is minor insulation structure. Major insulation structure, one between the grounded core and the LV coil to ground, between HV and LV coils, between top and bottom of the winding and yoke, between HV coil and tank, terminal bushings. In case of minor insulation structure, one between the conductors, between turns, between winding layers, between core laminations, between joints and connections. The core insulation that has to be placed between the core and the low voltage windings, and its primary function is to insulate the windings from the core, which thus to reduce the eddy current loss in the core. The core insulation is generally comprised of insulating paper or cloth impregnated with an insulating oil or resin. Individual conductors that are to be wrapped over by the cellulose based paper tape. The insulation as placed between the layers of HV and LV windings is mainly comprised of several layers of insulating materials such as kraft paper, mica or polyester film, aramid fiber paper, Nomex 900 series papers, etc. depending on the voltage level and application. However, thick Nomex 900 series paper or pressboard are usually being preferred as insulation for layer to layer or disc to disc winding configuration in cases of higher rating liquid immersed transformers. The dielectric strength of these insulating materials would have been significantly enhanced while they are being well impregnated with insulating oil or resin. Designing of the particular insulation structure that would have to play a crucial role in ensuring the perfect insulating barriers of the windings from each other and from ground till the expected lifespan of a transformer. Barrier insulation system is made to configure between the HV and LV winding layers for preventing any sort of insulation breakdown due to occurrence of high electric field between the windings. The barrier insulation is to be formed by a combination of insulating materials such as paper, mica, polypropylene film, and that are to be impregnated with insulating oil or resin for better performance. However, there may have the possibility to occur a surface partial discharge PD along the interface of solid liquid insulation. Here, the surface partial discharge that has to instigate along the interface of the mineral oil as liquid insulation and solid insulation such as cellulosic type and Nomex paper and pressboard. It's obvious that there would have a major disparity of permittivity between the isolating fluid, that is oil, and impregnated pressboard. Static electricity or electrostatic charge, that would be the phenomenal effect when surface potential of the pressboard material may have to increase due to accumulation of surface charge caused by the oil circulation inside the transformer. Surface charge, as accumulated, may eventually result in incipient discharges after a prolonged period of time. Such occurrence, once started, that would have been the most prime concern for deterioration of the life of a power transformer. From the CIGRE, that is CIGRE report, where it is stated that lowering the surface tension of the insulating fluid could reduce its electrostatic charging tendency upon contact with the pressboard material. Transformer bushings whose insulating structure would have to be designed as per voltage configuration and being suitably placed to facilitate the passage of an energized current carrying conductor through the grounded tank of the transformer. Bushings for the LV windings are made up of insulating materials such as porcelain, glass, or resin. Capacitance graded bushings that are to be designed for higher voltage ratings and are compatible to use for HV windings. Let's stop here, further to be continued at later stage. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.